Let's start the second session of today. And the first speaker is Professor Guenther Wunner, and he's talking about PT-exactly systems.
Thank you. Good morning. First, I'd like to thank the organizers as well for setting up this conference at this beautiful place, and also for giving me the opportunity to talk about results that my group has been thinking about over the past 4 years. My topic will be the question how to realize PT-symmetry in a real quantum system. I mean, PT-symmetry was conceived by Carl Bender in 1998 as an extension, so to speak, of Hermitian quantum mechanics. But experiments so far have only been dealt with in classical systems, optics in particular, waveguides, but also electromechanical constructions. But so far, to the best of my knowledge, there is no quantum system where PT-symmetry has been realized experimentally. That's the topic that I'm going to talk about. Now, our proposal that we're proposing several years in the meantime is to take Bose-Einstein condensates in a double-well potential with gain and loss, which would be a PT-symmetric situation, and there to verify T-symmetry experimentally in a realistic system. So the problem that arises with Bose-Einstein condensates as compared, for example, to waveguides, is that you have a nonlinear interaction between the particles. The short-range S-wave scattering uses a nonlinear interaction between the particles, the atoms in the Bose-Einstein condensate, and as a consequence, you not only have a non-Hermitian problem, but also a non-linear problem. This makes the situation more complicated. So PT-symmetry, as we have heard over the time during this conference, is the case where you have a Hamiltonian that computes with the parity and the time reversal operator. And the important thing to note is that if you have a complex potential whose real part is a symmetric function of x, and the geometry part is an antisymmetric function of x. Now, if you look at the probability current density that we know from ordinary quantum mechanics and look at the continuity equation for it, then normally on the right-hand side, for a vanishing imaginary part of the potential, you have 0. But now with an imaginary part different from 0, you have, if imaginary part is positive, you have sources of probability current density. So all things of the probability of presence. So this provides, therefore, an elegant way of describing open quantum systems with gain and loss. So now the proposal that I've already mentioned is Bose-Einstein condensate in a laser-generated optical double well, where you have particles injected in the left well, then you have a coupling between the two wells, and particles are ejected or drained from the right well. This is the physical picture within an effective description. In fact, there has been already been given a mean field description by Eva Maria Graf in 2012, using in a two-model approximation the two-state Gross-Bitajewski equation, which means that the time derivative of the coefficients of the wave functions in the two modes are given by this expression. You have the feeding in of particle at site 1, and the removing of particles in well 2. You have a coupling between the two, and you have this nonlinear interaction that I mentioned before, given by the value of the quantity g. Now, it's not that easy to remove particles from a Bose-Einstein condensate or to feed in particles, atoms. In fact, there have been experiments where you can remove particles by very sharp electron beams, and also by letting another Bose-Einstein condensate drop onto another one by inducing a radio frequency transition that causes the second condensate to drop into the other one. But that's not simple. So our proposal was then to here I give the station solutions of the two-mode model. There exist stationary solutions proportional to e to the minus ut, where mu is the chemical potential with real eigenvalues, as one can expect for a PT-symmetric system, with amplitudes given by this. This is the occupation number in each well, which is supposed to be constant, of course, and we have a phase relation between the two modes, which is given by the coupling and or the non-Hermitian parameter and the value, the strength of the coupling. Then the occupation number in each well is constant. The current density from between the two wells is constant, given by this term, and the correlations, which is the with the plus sign, is also constant. So stationary conditions. But as I said, it's not that easy to realize balanced gain and loss in real condensates. So our proposal was to embed the two-mode model in a four-well system. So we still have here the two-mode system. Now it's called psi2, a coupling between them. But now we have two outer wells, one psi1, which feeds in particles by a coupling constant J12, and the other one by taking away particles by dropping them into the outer well. So we have some sort of current flowing through the whole thing. So the idea was to simulate the non-Hermitian open two-well system, which is this one, by a time-dependent adjustment of the outer tunneling coefficients, so they may be time-dependent, and also the energy offsets. The question how deep or how high should be the minimum of the two wells. Of course, you would like to tilt it some way, so it should be up here and down here. So the time-dependent tunneling coefficients and energy offsets. So the goal was to obtain the behavior by embedding it into a four-well system. And if you write down the equation, this was the two-mode system we've already seen. Now we have a four-mode system with this Hamiltonian, the outer energy offsets, the time-dependent coupling constants I mentioned before. And you see, the gamma has disappeared from this equation. That's because we replaced it by the time-dependent energy offsets and the coupling. And if you can immediately read off a number of equations from here, for example, if you take the second line operating on this vector, you see that minus your j sub 1, 2 on operating on P1 must be equal to this, what happens here. So it's the I gamma psi 2 and so on. So can already relate quantities with each other. So the result was that we published in 2013, that I also presented 5 years ago at the Koch conference, is that by requiring that the two inner wells behave exactly as in the PT-symmetric two-well system, conditions can be derived or protocol can be devised, which allow for the explicit calculation of the time dependencies of both tunneling coefficients and the energy offsets. So the result was here, this is the occupation number of the two inner wells, in terms of the complete number of particles, so it's 50% each constant. So those are the outer wells. The outer one changes linearly, putting particles in the neighboring well, and the well on the right-hand side catches all the particles that have been injected into the system. And here are the control parameters. This is the energy offset, which are sort of well-behaved functions of time. And similarly for the outer and inner wells, the coupling constants also don't change very much. So everything seems to be fine, except for the point that we always met with the objection, well, this is mean field. A mean field description is nothing else than classical physics. So what happens if you add many-body, real quantum many-body effects? So the criticism was, will the behavior still survive in a many-body description? So the many-body description, the method of choice for this, is the Bose-Hubbard model, which has been used a number of times for describing bosons in optical lattices, so that is in laser-generated optical lattices in 1 or 2 dimensions. In our case, we just need 4 wells. So it has been set up was a paper by Yaksh et al. With Zoller and Sirac in 1998. So the idea is just 2 neighboring wells, as we had before. You have a particle or an atom in this well, and you have a coupling between the 2 wells. There may be an energy offset between the depths of these 2 wells. And so now you have 3 terms. The third one is just the energy offset, proportionate to the number of particles that you have in each well. The first one is the coupling between the 2 neighboring wells, given by the amplitude or coupling amplitude m prime. You remove a particle in well m prime and produce one in well m. And then you have a penalty term, so to speak. The particles have a repulsive interaction. So this is determined by the quantity u. If you add 1 particle in another well, you pay price for that. The energy goes up by this quantity. If it's just 1 particle, it doesn't contribute. So this is the model U of the strength of the contact interaction for Bose-Einstein condensates, and epsilon are the on-site energies. So now we will apply this model, or this Bose-Hubbard Hamiltonian to our system, and this means, so this is again the cartoon that I showed you before. Now the coupling constants between the wells will be time-dependent. So we have to set up a time-dependent Bose-Hubbard model, in particular for the outer coupling coefficients, J12, and the offsets, and similar for this one here. Okay, so determine that of such a system, if you have a many-body description, what you have to solve is the von Neumann for the full density matrix. So if you have 100 particles, you have to set up a many-body wave function, evolve it in time by looking at the full density matrix. A simplification is obtained by looking at the reduced density matrices. That is, you take the average of, in this case, of 1 creation and 1 annihilation operator, or 2 of them, and end up with what is called the single particle density matrix, on the 2 particle density matrix, and so forth, higher orders. And from the full density matrix von Neumann equation, you can subsequently deduce equations for the single particle density matrix, which is a function of the single particle matrix elements themselves, but also of the second order moments. And similarly, for the second order moments, you get an equation depending on the first, the second, and also on the third order density matrices. And the trick then is to formulate a BBJGKY hierarchy in the way that you stop after the second moments and approximate the third order density matrix by this clever expression. So then you only have the single particle matrices entering the equations, these 2 sets of equations, and the second orders. And all in all, you then have for the single particle matrix elements 4 to the square, 4 squared equations, and for the 2 particle density matrices 4 to the 4 possibilities, which ends up with 272 time-dependent coupled differential equations that you have to solve. So a note in passing is you can also look at the 2-model system that introduced before, that in the mean field description, you can also formulate a single particle density matrix or a higher density matrices. In this case, in the mean field description, it's just the product of size scar psi k star, so the complex conjugate times the other coefficients. Then the occupation number in the well is, of course, the diagonal element of this single particle density matrix. The current between the two wells is given by the coupling times this reduced current, which can be expressed as the 2 times the imaginary part of the density matrix element, the one particle density matrix. Similar for the correlation with the plus sign is the real part. So it becomes sort of important in what follows. So the idea now is, this was our original problem. We embedded in a former problem, and now we ended up with equations for the single particle density matrix and the two particle density matrices occurring here. And so we want to simulate this behavior by this equation, by this many-body description. So we have several requirements in order to put these two pictures together. One already I had already was in the original paper, in original equations, when I introduced the four-well system, that the coupling between well 1 and 2, the outer wells, times the current from well 1 to 2 must obey this condition, where gamma is the coupling constant in the original problem. Similar for the current flowing out on the right-hand side. Moreover, since in the two-well system there are no currents from 1 to 3 or from 2 to 4, we also always have this condition, which will become important now, that the coupling J12 times the sigma 1,3 plus this must be 0 at all times, because it doesn't appear in the two-mode problem. So the Hunnell rates, which are the couplings between the wells, follow directly from the comparison of the dynamics. So what happens? What about the on-site energies? So this requirement that I put just down should hold for all times. So the time derivative should vanish. And from this, you obtain an equation, a system of equations, of inhomogeneous equations of this form, which determines the offsets, the energy offsets of the outer wells. Now we have other coefficients appearing here, omega r and so far. The solution, the former solution, can be written down already with denominators, which later will cause problems if, for example, one of them gets 0. But so far, it's fine. When the abbreviations that appear here are given on this slide, which just impress you that it's not that simple to simulate the two-mode or the four-mode system in terms of a many-body dynamics. So, but the bottom line is the dynamics of any initial state of the many-body system can be now simulated, can be calculated. So far, now we have to construct initial many-body wave function, or find initial conditions for a many-body wave functions with some number of particles in the whole system. So far, we have these conditions that from the real part, the imaginary part of this equation vanish we had before. This is the imaginary part from a direct comparison of the dynamics, and we have also the condition that from the PT-symmetric states yield 3 real-valued constraints for the elements of the single particle density matrix, namely that the initial occupation in the two middle wells should be equal. Also, that the current between the two inner wells should be also constant, so given by the number of particles in the inner well, in the two inner wells, and also the correlation, the plus sign, which I told you at the beginning, obeys this relation in the two-mode model, is given. So, depending on the number of particles you put into the individual wells right at the beginning, you have an initial condition. So now, how to construct such a suitable initial state? A pure initial many-body particle state looks like this. So we have four well system. We have four coefficients for the four wells, and we have a Fock basis. So in our calculations, we'll have 22 particles. This means you can either put 22 particles right at the beginning into the outer left well, or you can put 21 there. And depending on it. So you can distribute these 22 particles as you will into these Fock states, and the superposition then gives you a total wave function corresponding to 22 particles in this sequence of Fock states. In the case of 22 particles, the Fock space already has a dimension of 2,200. So that's the reason why it didn't go to higher numbers, because this becomes awfully difficult. So the coefficients that you have at the beginning depends now on the bundle of particles that you put into the individual wells. And again, we have this phase relation that we still inherited from the two-mode problem. Okay, this was done, and in a paper that we published at the beginning of this year, and the disappointing result was that no quasi-stationary behavior can be found in the two inner wells. So, for example, what is plotted here is the particle number of the number of particles in the wells. The one is the N naught in this case is the one that is depleted on the left. This line corresponds to the outer well on the right. And then you see that for some time, the inner wells have almost exactly the same occupation number, it seems stationary, but then the particle number in the left well just goes away. In fact, the dotted lines would correspond to the mean field description. So for some time, we have good agreement with the mean field description, but not very far. And at time equals 10, this is in this case, it was 110 particles. This is when the left well is depleted and you can't feed any particles anymore in the system. Similarly, the currents between the wells can be kept stationary for some time, but not as long as in the mean field approximation. So, no quasi-stationary behavior, at least for all times, or at least for the time that the system is being fed with particles, can be found. So now the idea was to improve on that. So this was the pure many-body particle state by perturbing the pure initial state. What does this mean? We still have these coefficients for the 22 particles in the individual wells with this dimension of 2,200, but now we deflect these states by adding coefficients or numbers, random numbers, with a normal distribution. And normal distributions with mean 1 and variance depending on as you wish. So then, for these states, you can also calculate the initial values of the one single particle density matrix, the two particle density matrix, and then follow the dynamics just like in the case before. And so this is the numerical results with 22 particles, dynamics for the first order moments. Here we have, to the left, the number of particles in the wells. The violet one is this one. You see that it slowly decreases linearly, and on the right, and the right-hand well, it's slightly increases. And in the middle wells, we have each one particle in this case. So we have 20 wells in the 20 particles in the outer wells at the start, and one particle each in the inner well. Yes, please. Question. The initial state was we started with, in this case, it was 110 particles. You say we have 50 particles in the outer wells each, and then we have 10 let's see. There was 100 and something, yeah. Roughly was the same number of particles in the outer wells, in the inner wells, right? Yes, well, more in the outer wells. The phase is given by these conditions here, depending. Well, it's not in a real equilibrium because you have particles flowing in and flowing out at the other side. But just want to have that in the middle, it behaves as if it were a two-well, a PT-symmetric. Right at one end. Let's go. So it's just for a limited period of time. You would have to feed in other particles as well. In fact, there has been the extension of this would be to have four wells and another 4 wells in a circular arrangement. Then you can feed in all the time. Yeah, that's we didn't do so far. Yeah. Let's return to the discussion of the number of particles. So the outer well is decreasing in number of particles, the left one, the right one increasing, and in the inner wells you have constant number of particles. In this case, just 1 particle each. The same if you compare with the currents in the two-mode model and now in this many-body description, the dotted lines correspond to the two-mode model. For example, here the brown one would be 4, so it's identical over the whole period of time that we have. Same here. So the currents also are stationary. But, and also the coupling constant, the tunneling rates, are well-behaved functions up to a point where it suddenly blows up. And the reason of this can be traced back to the fact that the currents from the outer well to the middle, from the left and to the right well, go to 0, and they appeared in the denominators of this inhomogeneous the solution of the inhomogeneous equations, system of equations. And the reason for that is that we have decoherence in the problem, and we have neglected the higher moments. This is the moment in time where we would have to take into account the 3-body density matrix, for example. But we don't have enough conditions to adjust the parameters for the constraints for these. So at this moment, our calculation breaks down. The same then also holds for the offsets. The left one must be high at the beginning, the right one is low, then they approximate, they approach each other, and then they disappear. Finally, we've also looked at the purity of the condensates in the case of the two-mode model and then so at the beginning, discussed in the beginning, and this many-body 4-mode model. The purity is a measure of the mixedness of a state, and purity 1 in this case means it's a product state, and not a mixed state, and the 0 would mean it's a completely mixed state. You see that in the case of the 1, so these are values very close to 1. In the 2-mode model, the purity remains almost within the numerical uncertainty 1, while in the 4-mode many-body description it slightly decreases by this coherence, but since we have chosen a mean for the random numbers of the normal distribution of equal 1, and only a variance of 0.008. So it's not a big deviation from the pure state. That's the reason why over this time the purity, this almost remains a pure state, even though we now can realize the PT-symmetry of the inner well as we wished before. So this already brings me to the summary. The goal was to reproduce the PT-symmetric Bose-Einstein condensate in the 2 inner wells in a many-body description in terms of a Bose-Hubbard model with 4 wells, time-dependent energy offsets, and coupling coefficients. We found the time dependence for the tunneling rates, the left and the right, and also for the energy offsets, and could determine them. And we used mixed initial states, which perturbed the pure mean field initial state, and had to fill the constraints imposed by the comparison with the 4-mode mean field or even 2-mode model. And in the end, the behavior of the PT-symmetric BEC in the inner wells could be described in the first order of the many-body description hierarchy. Now, there are, of course, 2 questions that can arise. The first is, what about the second order density matrix elements? How do they behave? One can calculate them as well. So this is then the fly in the ointment, that the many-body description is the blue one, and the mean field description, the two-field, 2-mode system, this one. You see, they are on the same order of magnitude and constant, but they are not identical in all cases. And this of course, this would mean that we have to extend the system either to add more reservoirs or in the outside, or to close the system by adding 4 other wells, so that you have current flowing round about all the time. And the other question that always arises when I talk about this topic is, now what's the experimental situation? Well, we have talked, of course, to experimentalists. First of all, they always have their own experiments and their own priorities where they think that should be done first. And then I have always heard the answer, well, if it has been proved in optics, what's the use of doing it in quantum mechanics again? So that's the status. We are still trying busy. Ziad Muslimani, who is a frequent visitor to these conferences, has promised to ask a friend in Amsterdam, but let's see. Okay, with that, I'm done. Thanks.
Hello. So your four-level system is Hermitian.
Yeah, right. Exactly.
And another question. Like you were saying, this is the quantum version, right? So at least the one thing is it should have this quantum fluctuations somewhere.
Exactly.
So,
but that's incorporated in the many-body description.
I see.
It's different from the situations that were discussed before in this conference, where it was always said if you have dissipation, you must have fluctuations. But the fluctuations are built in automatically by looking at the many-body.
Is your density matrix in Lindblad form?
It is, yeah.
If that comes out naturally, or you have to manipulate it?
Well, that's the alternative description that we've also followed. So we will Lindblad superoperators to look at this problem. There are 2 methods, the Lindblad formulation and the Bogoliubov back reaction method, which we preferred in this case.
But they give basically the same results?
They yield basically the same results, but this description is simpler than the one with the Lindblad form, which was even more complicated.
And did you calculate your condensate fraction as a function of time?
You mean?
Well, when you diagonalize your one-body density matrix, the eigenvalues will give you the fraction of particles in a condensate. You started off with a pure condensate?
Yeah.
And did you calculate how that behaved as a function of time?
Well, that's contained in the purity of the state. So it, as you saw, the purity. Let's see. It decreases, but it's not too much. So it remains pure condensate, even if you perturb it only slightly. Almost, you see the quantity is close to 1.
Comment? I have some questions. So if I understand correctly, so you need some perturbation to obtain the PT-symmetric system. Yeah. And could you tell me the strengths of the perturbation you introduced? Could you tell me the strengths of the perturbation?
The strength of the perturbation, well, as I said, the perturbation is given by a normal distribution of the random numbers that we pick from, and the mean is equal to 1. Variance 0 would mean we still have the pure initial state, and we just added a small variation, 0.008, so a variance of 0.08. So it's a very sharp normal distribution that we pick our random numbers from.
Comments? So if not, let's thank the speaker again.